No questions on the precipitation reactions? Okay. So this chapter, reactions in aqueous solution, chemists almost always do their reactions in a liquid just because that's the most convenient way to do them. Gases have to be corralled in chambers, and if they leak, they might be toxic. Solids don't really react. You have to at least dissolve them in something to get them to react. So that's why we're covering so much. That's why the name of this chapter is Reactions in Aqueous Solutions, because that's almost always what we do as chemists. So we covered precipitation reactions. That involves ionic compounds. So this next section, acids and bases, these are essentially ionic compounds, but they're special ionic compounds. And you might remember OH negative is one of the polyatomic ions. I'll say H plus. H minus you would have called hydride. If it was in an ionic compound, like that would be sodium hydride, and then hydrogen is negative. But hydrogen's a little weird. It's sometimes positive, sometimes negative. Sometimes it's gained an electron, and sometimes it's lost an electron. And so H plus is the case where it's lost an electron. But when you see those, think acid and base comes from OH. That's the hydroxide ion. We call this, you could call it hydrogen ion. But in terms of constructions of the atoms, hydrogen all the way at the top left, it has one proton in the nucleus, one electron around it. If it gains another electron, you have that, the hydride. If it loses that one electron that it has, then it's this, H plus. But if it loses that electron, there's really nothing left of it except for that proton. It really is just a bare proton once it loses that electron. So H plus, we sometimes call this proton, the proton. I usually say that instead of hydrogen ion. But it's a unique charged atom in that sense that there are actually no electrons on it. It's just one little bare proton from the nucleus. So these are the hallmarks of acid-base, concept of acid-base. So proton and hydroxide ion. And having said that, these are essentially ionic. Let me go back to there it is. This solubility guidelines. This chart, let me point out, there's the OH. So all of the chemical compounds that we refer to as bases, so that's literally what this is referring to. If it's something OH, then it's a base. And notice, if I go down the left side of the periodic table, that first column, sodium, potassium, etc. This is how I would make the ionic compound with the negative OH. So Li plus, Na plus 1, K plus 1. So those are bases. These ionic compounds are actually bases, strong bases. And I'll move over a column. We've got beryllium, magnesium, calcium, strontium. beryllium, magnesium, calcium, strontium. And that's what you see here. The alkali metals, that's the first column. Calcium, strontium, and barium. Calcium, strontium, barium next. So of course these would be, since it's +2 ions now, I have to do this. Put the 2 on it. I've left these off because you'll see here, anything hydroxide is not soluble except for these. I guess I should mention so ammonium hydroxide. So I'll just add that one here. NH4OH. So I'll throw that one in here too. These are all considered strong bases. Magnesium's not here in the exceptions, but the truth is this one is not soluble, so it doesn't act like a base. And this one's partially soluble, so it will still act as a base when you dissolve it in something. This one's a 2 on it. So there's all your strong bases. I think we would say this, I think we would still say it's a strong base, but it's partially soluble. So bases. NH3, which should look a little weird because it doesn't have OH on it. And this is a weak base. But I'll come back to NH3. It's an odd one. But essentially you can think of bases as something that, oh, this always happens in water. Don't forget, literally part of the definition of acid base involves water. Like I have a pure beaker of water and I go get a little jar that's got some lithium hydroxide in it or sodium hydroxide, solid, and I dump it in and it dissolves. That solution is now basic, or we might just say the solution is a base. But using NaOH as an example, just like I was talking about with the precipitation reactions, the ionic compounds that you would put in something and it would dissolve, you really just have a bunch of this. Let's just say H2O. I'm trying to mimic a solution here. So floating around in the H2O are these ions split out. That's what a basic solution is. And really, these are sort of analogous to spectator ions, because I could have achieved a bunch of OH in that solution if I had used KOH or calcium hydroxide or any of these. So it's not really the Na we're paying attention to, it's this. It's all these OHs in the H2O that make it a basic solution. So these are bases. You can have them in a solid form. When you dump them in water, you now have a basic solution because you have a bunch of OH floating around. Definition of a base. Acids, still looking up here at this chart. If I want to talk about acids, so I'll first point to Cl and Br here. So now we're on the other side of the periodic table. We're in these. Really not hydrofluoric, but chlorine, bromine, iodine. Chlorine, bromine, iodine, really the main ones. So hydrochloric acid, hydrobromic acid, hydroiodic acid. So there's three strong acids. Other acids you can get, so I'll say strong acids. I'm going to put back over here. So all of those first and second columns, OH, are all strong bases. I mentioned NH3 is a weak base, and I'll come back to it. So strong acids, another strong acid. So I'm back here still on the solubility. NO3. So first notice you've got H plus and Cl minus. Those come together to a neutral compound. Same with Br. Those come together to make HBr. I the same way. And then I'll add to this a couple more. You've got the NO3 and the SO4. NO3 is negative, SO4 is 2 negative. So we also have, if I add an H plus to this, then I have this compound, neutral compound. Called nitric acid. Since this is 2 negative, I'm going to have to put 2 H pluses on there. Sulfuric acid. There's a list of these down in that chapter. I was going back to the solubility chart. So these are strong as well. So I'll come back to what we mean by strong and weak. Actually, I'm there. So I guess I'll stick these over here. HNO3, nitric acid, sulfuric acid. I guess that's not in this chart, but there's chloric acid. And there's HClO4. So you remember the ClO negative? I didn't make y'all memorize that, so maybe you don't remember it, but it was in that janky list of polyatomic ions. So you have chloric acid and perchloric acid. So I mentioned those two. Chloric acid, perchloric acid, where was I? I'm going to put those over there. HNO3. Okay. One other ion that's in this chart. This is the acetate ion. And I'm going to draw it out. This is negative right here. So that's that CH3COO negative, CH3COO negative. If I had an H plus, I could stick it on right here, and that would make this neutral. The positive and negative sort of cancel each other. That okay, that's acetic acid. That is an acid. Now let me remove this again and put the negative on it. That's the acetate ion. That's the acetate ion. That's what's in that chart. But if I put a H plus on it, in neutral, I'm just going to write OH. It's very common to do that. I mean, I should technically draw a line to show that it's bonded, but OH is such a common structure. I'm so used to writing it like that. I just want to do that. So now that's acetic acid. So this is a weak acid. And the reason that it's weak, what we call weak, is if you put that in water, if you put these in water, they do exactly what I've described before. They come apart in ions. Every single HCl molecule, if you put it in water, will split apart into a Cl minus and an H plus. If you put a weak acid in water, and I believe this is the only example you're going to see, this does happen, and they float apart, but it only happens a little bit. Most of the molecule that you put in there, most of the molecules that you dump in your water stay like this, and only a very small number of them dissociate like this. So that's why we call it weak. It only dissociates a little bit. Most of the molecules that are in the water stay like that. They remain acetic acid. But some small number of them will break apart into the proton and the acetate ion. So that's a weak acid. Acetic acid, weak acid. So the weak base, so it partially dissociates. And I mentioned when I said this is a weak base, it does the same thing, it only partially, it only makes a few OH negative ions. But really what happens, this one's just kind of weird, it's an odd one, but it actually reacts with an H2O molecule, and it becomes NH4 plus OH. It's grabbed one of these H's, so now it's NH4. It becomes positive and OH negative. So you get these ions if you put ammonia, NH3, in water, it will become ammonium ion and OH to a small degree. Most of it stays like this, and a tiny amount of it becomes this. So weak base. It only makes a little bit of OH in water. So it's weird in that it doesn't have OH on the structure, but it forces OH to show up in the water just because it's already water. There's already OH in there, H2O in there. So it pulls a proton off water molecules and then water, what's left behind is an OH from the water. Okay. And acids are sometimes referred to as proton donors. You can think of it as, I put this in water and it donates an H plus to the water. But really, ultimately that H plus goes somewhere. So it's donating it somewhere. Bases are referred to as proton acceptors. So that's where the H plus is donated to a base in the solution. But that'll be more obvious when I do this next thing. So acids and bases, this is just sort of the fundamental definition of what acids and bases are. Neutralization is basically an acid-base reaction. So if I wanted to show a reaction, this is just, I think your book calls it dissolution. Some books call it dissociation. Maybe you should just think of it as dissolving. When you put the NH in, it dissolves like that. But an acid-base reaction is when you put an acid and a base together. And I'll use the canonical example of something like this. I'll do strong NaOH and HCl. If I went reaction, one of the hallmarks of acid-base reactions is you almost always get a water molecule. In the same way that we had the molecular equation and the complete ionic equation and the net ionic equation, this you would call the molecular equation. Here's the complete ionic equation, or at least on this side. I should be saying aqueous, AQ, literally meaning it's in water. So I should say AQ here as well. Cl minus AQ Na plus Aq. And I haven't done the other side of the equation yet, but I think it'll look obvious when I do. So I would say this is the complete ionic equation. And there is a net ionic equation. Let me write the rest of it here. What you get is we'll just say L for the H2O liquid. AQ means aqueous, means dissolved in water. L means it's in a liquid state. S means it's in a solid state. We covered that last time. So what you're getting is split these ions out, split these out, and now this H plus and this OH negative is what makes the H2O. And then you get NaCl out of these. But truthfully, they are split apart as ions. They're not together like that. We're out of space. Na plus. So you have sodium ion floating around in the water, and a chlorine ion floating around in the water. And we just leave the H2O like that. The net ionic equation is actually just this. Aqueous. That's the net ionic equation. So acid-base. Well, acid-base reaction, another way of saying a neutralization reaction. So you create a water molecule, and then this other thing, it might not surprise you that I would call that salt. You might already know that NaCl is table salt, what we have on our tables and what we eat. But really, any two ions that I could have used here, I could have used Br here, I could have used lithium here. Those are all called salts. More generally, chemists call those salts, not just NaCl, because they can be made this way. They can be made from the halide, the Cl, Br, or iodine, acid, and then one of the bases. So it doesn't have to be Na and Cl, but anything that you can do this with, for instance, I could have done this. LiBr. That's a salt as well, because you can make it with the halide acid and the alkali metal salt, or alkali metal base. Makes sense? The salt, acid base, okay. Fundamentals of acid base. I guess I can go back to the acid base chapter. So there's a list. I've mentioned all of these. The acetic acid is the weak one. I'll mention this. Protic. I mentioned nitric acid, and I mentioned H2SO4. So if I just show the dissolution process, I would just say this. And now I'll show the dissolution process for this one. I'm going to say H plus H 4 minus. This is called a diprotic acid, and this is called a monoprotic acid for obvious reasons. The proton referring to the proton. This one will further dissociate into H plus, so 4, 2 minus. So ultimately, you can get both of those protons to come off. Most typically, the first one is what happens, and you have to get a really, well, you have to have these going somewhere, say to a strong base, to get the other one to come off. And I'll mention this one too, phosphoric acid. PO4 is 3 minus. So you can get 3 plus charges on it. And so now we've got a triprotic acid. And it will come apart in stages too, like that, 3 different stages. The first proton will come off. I mean, you'll get this H2PO4, 2 minus. And then that can come apart into H plus HPO4 negative. And then that last one can come off, and I'll have H plus PO4. I did that backwards. This should be 1 negative. And you pull another one off, and then it's 2 negative. And then the last one comes off, and you've got your 3 negative back. So triprotic acid. So here they're just showing the 2 stages of the sulfuric acid. I didn't mention the word electrolyte when we did when we met last time. If you have these ions, positive and negatives, floating around in water, and let's say this is just a beaker of water, but let's say it's got Na plus and OH minus ions all over in it. And you put a positive electrode and a negative electrode, like literally electricity. Electricity will flow. The positive ions will float towards the negative pole, and the negative ions will float towards the positive pole, and that's what we call an electrolyte. It'll actually conduct electricity. If you were standing in a creek, it's funny I said that. This actually happened to me when I was a kid. Standing in a creek while it was raining, and me and my friend were standing there, and the lightning hit, and we literally felt a strong bolt go through us, and we hopped out of the water and went running home. Didn't kill us, but the only reason that we felt that is because natural streams have a lot of ions in them. They have a lot of magnesium and sodium and stuff. Pure water won't conduct electricity very well, but natural sources of water will. So we would call this an electrolyte solution. Any of these ionic compounds that dissolve in water that have ions all in it, you would call that an electrolyte. So chapter mentioned it, so I'll mention it. And acids and bases are electrolytes as well. I think I covered this. There's the ammonium. This chart just gives you some strong acids and strong bases, but this is essentially what I just described about strong acids and strong bases, the ones I mentioned. So the strong acids and the strong bases make electrolytes, and the weak acids and weak bases make weak electrolytes. And then anything else does not make an electrolyte. But let me mention the acetic acid again. All right. So here's hydrogen, but they're on carbon. These don't come off in water. These literally stay stuck to the carbon. So this is not acidic. Or let me do something else. Let me do this. This molecule, that's not an acid. You see H's all over the place. Don't be tempted to think those will come off when you put that in water. This is actually a gas, but if I did something larger, that's a liquid. That's not an acid. None of those hydrogens come off if you put that in water. Similarly, if instead of an H there was an OH, Neither does this H come off in water, nor does the OH come off in water. This is called an alcohol when you have just an OH like this. So that's not an acid or a base. It's specifically, the weak acid that I was referring to is specifically when you have this. And it's okay, we won't talk about them, but even a long chain like this, as long as you got COOH, that's a weak acid. But it's got to have this whole structure for it to be a weak acid. Just to be less confusing, there's the acetic acid. That's an acid because you really need this whole structure here for this hydrogen to be loose enough to come off in water. So that's what this is referring to. There are some compounds that don't dissociate at all.
So is it acetic acid an electrolyte?
It's a weak electrolyte.
Okay.
Yeah, weak acids, weak bases are weak electrolytes. This chart's saying that any ionic compound that's soluble in water is a strong electrolyte. If it's soluble in water, there's no such thing as a weak electrolyte. I don't think that's strictly true, but we can go by this chart. And so for molecular things, strong acids are strong electrolytes. And weak acids and bases are weak electrolytes. Meaning they'll